The single operation that the x squared function performs is squaring, right? So it squares its input. So if we, in terms of order of operations, if we do something to the input before we square it, thank you. So any operation that happens before doing that one operation that your function is defined by, that's acting on the input of the function. Whereas if we do the squaring operation, so we start with x, we square it, and then we subtract 2, then that's acting on the output of your function. And so whether you're acting on the input or the output is important because it determines what direction the transformation happens in. So if it's a horizontal transformation or if it's a vertical transformation. So if I want to shift the graph up k units, what should I do?
It should be on the output.
Right, we're going to add to the output, right? So, which makes sense because the y values are the outputs of the function and the x values are the input. So it makes sense that we would, if we act on the output, it would have a vertical effect. So we're going to add k to the output. So if we square first and then add 3, that shifts x squared up 3 units. And then if I want to go down, what should I do?
Minus.
From the output still, right? So subtract. K from the output. So if I start with x, square it, and then subtract 3, that's going to shift x squared down 3 units. Okay, now what if I want to go right?
And subtract 2 from the input.
Yeah, we would subtract from the input, right? Left and right is the x value, and so we want to act on the input of the function. And any transformation that's horizontal always does the opposite operation of, or the opposite direction of what the operation seems to indicate. So that's why we subtract here. H from the input. So the way that I think about it is like, if we have something like this, say, if I gave you y and you wanted to find x, you would have to subtract 5, right? So you'd have to do the opposite of adding 5. Whereas if I gave you x and you wanted to find y, you would actually add 5, right? So for x, we're always doing the opposite operation. And for y, we're always doing the operation that's in the function. So all horizontal transformations seem to do, like I said, the opposite of what, or the opposite direction of what the operation seems to imply. So if I start with my input, subtract 3, and then square it, that shifts x squared right 3 units. And so then to go left, I should do what? Yep, add to the input. So again, starting with your input, adding 3, and then squaring, we'll shift x squared left 3 units. So what if I want to flip it? So across the x-axis is here, so reflecting across the x-axis, we'll go from here to here.
Would you make it negative on that in the front of the parentheses?
Right, so acting on the input or output?
Output.
Output, right? Because if we go from here to here, what's changing is the y values, right? The y values are becoming negative. It actually turns out if you multiply the input by -1, it doesn't change a thing, right? Because negative x squared is the same as x squared. Like if you square a positive and a negative, you get the same thing. And if you think about the parabola, if we were to flip it horizontally, like it'd be exactly the same because it's symmetric, right? So multiply -1 by the output. You could call that negative, like the 1 doesn't necessarily need to be there, but it's kind of helpful in noticing that you have to like square x first and then multiply by -1. And then if I want to stretch or compress it vertically by a factor of a, what should I do?
You multiply or divide the output.
Uh-huh. So we multiply a by the output. So for example, like g of x equals 1/2 x squared compresses by a factor of 1/2. So you'll notice the only operation we're doing in the horizontal direction is shifting, and that's just because you can achieve any horizontal stretch or compression with a vertical stretch or compression, and computationally it's easier to work with the output than with the input because you don't have to worry as much about like if you're adding or subtracting first and then like the order of it is backwards when you do it with the input, and so your order of operations gets a little hairy. So we will do all of our stretches and compressions vertically, right? So if we stretch it, so when we do a stretch, it's like we took the vertex, so that point 0, 0, where it turns around and like nailed a rubber band, and then you're pulling, right? So that stays in the same place, and then you're pulling it up or you're smushing it down, which makes it look wider or skinnier, right? Because it's hard to notice that it's taller or shorter because it goes up to infinity either way. So when we look at it visually, it kind of looks like it's narrower or wider, but in reality, we're either pulling it or smushing it vertically to achieve that. So in general, if we take our x squared graph, this point right here is called the vertex. And on the x squared graph, it's 0, 0. And notice like the vertex isn't affected at all by shifts, right? So, or sorry, by stretches, because multiplying by 0 still gives you 0. And so the new vertex is going to only tell you about shifts up and down or left and right. And so if we look at a graph, its vertex will tell us what the horizontal and vertical shift is. And then this point right here on the graph of x squared is 1, 1. And so if we look at So 0, 0. When it's stretched or compressed, that point becomes 1a because 1 times a. So if I multiply my y value by a, I'm going to get a y value of a. So we can look at just this distance right here to figure out what our stretch or compression factor is, even if our vertex isn't 0, 0. So even if we've shifted it around, if we look 1 unit to the right of the vertex, that distance from, or that vertical distance will always tell us what our stretch or compression factor is. So if we look at k of x for 7, has it been shifted? Left or right? Up or down? No, because our vertex is at 0, 0, right? So right here. And so I'm going to look 1 unit to the right, which is this point right here. And what's this distance? 3. So that's my stretch. And then I also have to flip it, right? So I'm going to take my output, which is x squared, multiply by a factor of 3, and make it negative to flip it. What about j of x? Has that been shifted? It has, right? So my vertex in this case is the point 1, negative 3. So this is right 1. And down 3. So if I want to go right 1, I'm going to start with my input, which is x. I have to subtract 1 before squaring. Then I square and subtract 3 to go down 3. And then I want to think about my a. So again, I'm going to look 1 unit to the right of my vertex. And what's this distance right here?
Half.
I guess I shouldn't call it a stretch. It's a compression, but it doesn't really matter if you call it a stretch or a compression because the value of a determines if it's a stretch or a compression. So 1/2. So the order that I write these in is a little funny because it doesn't actually go with order of operations. Like in order of operations, you would multiply by that 1/2 before you subtract the 3. But because that 3 isn't affected by the stretch, it's just easier to look at the shifts together and then look at the compression separately. Does that make sense? Okay, so then let's do these guys. If I want to make the graph 4 times as tall, what should I do? So our output times 4, and is shifted up 1. I'm going to add 1 to the output. Good. So we start with our input. We're not doing anything horizontally, so we square it. Multiply by 4, add 1. What if I want to shift it 3 units right? So input minus 3. And then to reflect it, times what? Output or input?
Output.
Output. And in general, like I said, we will always do all our stretches and compressions in the vertical direction. So the only thing you'll ever multiply by is the output. Like you'll never have one where you multiply by the input. So in general, if you know that the operation you have to do is multiplication, it's always by the output. So we're going to start with our input, which is x, subtract 3 from it, then square, then multiply by -1. Okay, you guys try C and D. Go ahead and flip to the second page. And how about the first 2 rows, graph f of x. The third row, Finn's row, graph g of x. And then the row by the windows, graph h of x. Keep in mind, you don't have to do anything to the function in order to graph it. Like, you don't have to distribute or anything in order to plug numbers in. You just want to like make a table, just like we've done before to graph the functions. Pick a bunch of x values and plug them in. Like, there's no need to like multiply things out. Just punch it into your calculator. So this one works pretty nicely if you go up to 3. You could do it going just up to 2, but it's a little more complete if you go up to 3. And for the first one, feel free to use transformations if you so desire, rather than plotting points. Whoa. Okay, that's wobbly, but no, we'll just let it roll. Okay, so these are all the same. The functions are just in different forms. So if you were to multiply this out and simplify, you would get this. And if you were to factor g of x, you would get h of x. And if you were to do like -2 times x minus 1 times x minus 1 plus 8 and multiply that all out, you would also get g of x. So these functions are actually exactly the same. They just look different because they're in different forms. But it's just like we've seen polynomial, we see how we can go from polynomials from simplified to factored and back to simplified, right? So that's all that's happening here, is that we just have the same expression in a different form. So let's look at some characteristics of our graph. What is the vertex?
1, 8.
It's 1, 8. Good. So that's this point right here. And which form of the function do we see that point in? A 1 and an 8. Yeah, in f of x, right? Because this is the one that is a result of the transformations, right? And remember how we said that that point 0, 0, the vertex, isn't affected by multiplication. And so that vertex is, if we go right 1 and up 8, that takes the point 0, 0 to the point 1, 8. What's my stretch factor? 2. If you wrote -2, that's totally fine as well. Technically, the stretch is a factor of 2, but sometimes it's nice to have the negative because it reminds us that we're also flipping it. Does this function have a maximum or a minimum?
Maximum.
Maximum. where in our functions do we see that stretch factor? Or which one do we see it in? That 2.
Looks like it's kind of an all of them.
It is, yeah. So that this leading coefficient is the same in all forms of the function. So that's kind of handy because it gives us information about if it opens up, if it opens down, which in turn tells us if our vertex is a maximum or a minimum, right? If it opens up, our vertex is a minimum because it's the lowest point on the graph. And if it opens down, our vertex is a maximum because it's the highest point on the graph. What are my x-intercepts? Good. And where do I see those? Which form of h, right? I should say gives x-intercepts. Those aren't actually the x-intercepts, but we can get them from that, right? It's the opposite of those numbers are our x-intercepts. What about the y-intercept?
0, 6.
Do we see that anywhere?
Yeah, in G.
Yeah, in G. So remember when we talked about linear functions, that b was our y-intercept, right? The constant term in mx plus b. Well, it turns out that that's true for all polynomial functions. The constant term will always give you your y-intercept because when you plug 0 in, all the terms that contain a variable just become 0, and you're just left with that constant term. Be careful not to mix it up with this, right? Like if you plug 0 into f of x in that form, this does not become 0. Right, because 0 minus 1 is -1, not 0. So you're not multiplying by 0 there. So you can't just grab that 8 and be like, that's the y-intercept. It has to be in that general form where it's all simplified and multiplied out and like terms are combined. Where is the function increasing?
Negative infinity to 1.
Mm-hmm. From here to the vertex, and then where is it decreasing?
1, 2.
Yeah, from 1 to infinity, so after the vertex. So these are our 3 basic forms of a quadratic function. So the first one we call general form, and that's when this expression is fully simplified. So we've distributed combined like terms. And the only thing we really get from that is our y-intercept. I mean, we can get more points, but we have to do more work to get them. So in this case, our y-intercept is 0c. And then factored form, as the name implies, is when this expression is fully factored. And from factored form, we can get our x-intercepts quite easily, right? If we set that equal to 0, we get x minus m equals 0. Solving that just gives us m. So m0, and then same for x minus n. And n0. And then standard form, well, that minus h tells us we're shifting to the right h, and the plus k says we're shifting up k units. So 0, 0 is going to go to the point hk. And realistically, we don't often get functions in standard form, right? When they're given to us, they're usually in general form or factored form. But standard form is really helpful in writing functions. So if we're given characteristics and we have to come up with the function, if we know the vertex, then like we have like more than half of that already, right? And you just have to figure out what A is. And so although standard form doesn't come up a lot like in practice as far as like when you actually like are given a function, it is really useful in writing an expression for a function, which we'll do here in a second. And then if A is positive, what does that tell us? So if that stretch factor is positive, it opens up, right? So like so. And that tells us that our vertex is a minimum. And if it's negative, it opens down, and so the vertex is a maximum. Right? Because if you are feeling positive, you smile. And if you're feeling negative, you frown. It's the cheesiest thing I've ever said in my life. Okay. We're going to skip this one because it's really basically the same as what we just did, so that we have time to do these guys. So here we're giving characteristics of the graph, and we want to write a function. So the first thing I notice is that I'm given the vertex. So in general, when you're writing a function, you look at what you're we'll never use this one. We'll never use general form to write a function. But if you're given the x-intercepts, that tells you you should use factored form. If you're given the vertex, that tells you you should use standard form. So the things that we easily get from the function are the same as the things that tell us which form of the function to write it in. So since we're given the vertex here, I'm going to use standard form. So we're going to start with f of x equals a times x minus h squared plus k. So in the vertex, this is my h, this is my k. And so we'll just plug those in first. So f of x equals a times x minus 4 squared plus 1. And just be careful with the sign on your h. The sign is always the opposite of the sign of of your x-coordinate, right? So if my x-coordinate was negative, that would be a plus. And if my x-coordinate's positive, that's a minus. Any ideas how we could find a?
Do slope point form with the vertex and the point.
So I like the idea of plugging the point in. We can't use point slope form because it's not a line, right? So it's not linear. But we can plug that point into the function that we already have and solve for a. If that point was 1 unit to the right of my vertex, we could just use the distance between the y values. But because it's not a line, it's not like every time you go over 1, it changes by a, right? It's only true of that first point because it's not a straight line. So, but we can take our input and output and put them into the function we already have and then solve for a. So if my output is -7, my input is 8, and then that makes a the only unknown. So I'm going to do 8 minus 4. And then we have a times 16 plus 1. Be careful at this point because it's really tempting to add 16 and 1 because of where the 16 is. But notice that's 16 times a, right? So like that multiplication has to happen first. So this is really 16a plus 1. We can't write it as like 17a because the 1 doesn't have an a, right? Those aren't like terms. And so that's going to give us -8 equals 16a. And then we'll divide by 16 on both sides. And simplify. So a is going to be -1/2. And so then we can write our function. So f of x equals our a is -1/2. X minus 4 squared plus 1. So you don't want to leave like that 8 and negative 7 in there. We just plug them in to find a, and then we go back to the general formula of the function. Make sense? So start with your vertex and then plug your other points in to find a. You guys try that second one. Everybody get that? No? So this is our h and k, right? So we have f of x equals a times x plus 3 squared plus 6. So that 3, we take the opposite sign of our x coordinate. And so then our output is 9 when our input is 3. So 0 plus 3 is 3. Squaring that gives us 9. So we have a times 9 plus 6, which is 9a plus 6. So subtracting 6 gives us 3 equals 9a. So a equals 3/9, which equals 1/3. You see it, Levi? Where it was? Okay. Okay, so tonight, you have just my math lab, so you have plenty of time to do the homework corrections that I just gave you back. I wanted to really quickly just comment on one thing on the homework corrections. If you think of f of x equals y, just as a general statement, then anytime there's a number in here, you're given x, and you don't know y because you don't know what's on the right side of the equal sign. Whereas if you're given the number on the right side of the equal sign, they are giving you y, and you don't know x. So that was one that a lot of people got mixed up, like if you're looking for x and y. So just remember, like, what's on the right side of that equal sign is always your y value, and what's in the parentheses is your x value. So if they give you a number in the parentheses, it's always an x, and vice versa. Okay, have a great Monday, guys. See you tomorrow.